We welcome Dr. Mohammed Zidane. Dr. Mohammed Zidane is an associate professor in the AI department at the Faculty of Computers and AI at Gharda'a University, Egypt. He holds granted patent from the US Patent Office for his invention of the fastest ever main memory for quantum computers, and has filed an additional 10 patents for innovations in quantum blockchain, quantum cryptography systems, and the quantum database systems. Dr. Zidane has published numerous papers in high-impact journals in the fields of quantum machine learning and quantum computing, and he serves as a reviewer for over 20 international journals and supervises more than 20 master's and PhD students, both in Egypt and globally. Okay, thanks.
Hello. First of all, thank you, Dr. Taha, for having me in this interesting event. Today, I'm talking about inventions and advancements in quantum computing. I'm trying to make some discussions as Arabic, another discussion as English, but my research group is Professor Muntasir Qasaima, Professor Hisham Naish, Professor محمود عبد العاطي. امبارح كان احد الناس بتسال في الجروب بتاعت الهاكاثون what about quantum engineering jobs. احنا مستقبلنا ايه في الكوانتم؟ انا كباحث لسه بادئ او كانجينير لسه بادئ، انا مستقبلي ايه؟ هاكل عيش في المجال ده ولا مش هاكل عيش؟ وكان رد بعض الناس كان محبط. اوكي. But the most interesting thing today, we have the first quantum computing product in the Middle East. We developed the first quantum computing product in the Middle East. You can scan this QR code. Indeed, this graph generated by NVIDIA shows the required resources for the development of cutting-edge artificial intelligence systems. This graph explains a critical challenge. As large language models are training in ever-expanding sizes of datasets, the required resources in terms of the computing power and storage capacity of main memory increase exponentially. So, without a breakthrough in the development of cutting-edge for developing computing resources and memory technology, the advancement in quantum computing and artificial intelligence technology will be very slowly and costly. So, some researchers are motivated to develop what's called quantum machine learning. And there are many misconceptions and there are many mistakes in quantum machine learning. Why? والحقيقة إن بتجيني مسج كتير على الواتساب بتسألني إحنا إيه المشاكل عندنا في الكوانتم ماشين ليرنينج والكوانتم اي اي. بعض الريسيرشرز بيطبق traditional and classical machine learning on quantum computing to optimize the topology of quantum circuits, and then they publish their work as quantum AI. This is incorrect. This is not quantum AI. Here you have a classical machine learning وانت بتطبقه على quantum circuit. So the training process is performed for classical machine learning, not quantum machine learning. Okay? So this is not quantum machine learning. Okay? This is totally classical machine learning, not quantum machine learning. Okay? The second thing is that for variational quantum machine learning, there are many tricks. The researcher swamped interrupts. ايه اللي بيحصل هنا؟ انت بيكون عندك الداتا سيت بتاعتك متخزنه اساسا في الكلاسيكال ماشين ليرنينج، في الكلاسيكال رام سوري. انت عندك you have classical machine learning and stored in classical RAM. Then you encode the data from the RAM into qubits. Then you try. So here the reading process is classical complexity. This is what destroy your work. The complexity here is classical complexity. So when you encode your data set into qubits, then you apply some ANSAT, okay, or some variational circuits. Then you make measurements. Then you apply classical machine learning algorithm, what's called classical optimizer. So what is the advantage? No advantage. وللأسف أبحاث كتير جدا منشورة في باسم إن إحنا بنحقق الكوانتم أدفانتج. للأسف. وهوضح إيه السبب في نشر الأبحاث دي. ليه الأبحاث دي اتنشرت؟ طيب. لما نفحص الأبحاث دي مش بنلاقي أي كوانتم أدفانتج من ناحية التايم كومبلكسيتي. ولا ميموري ادفانتج. بعض الباحثين بيدعوا ان هم عملوا ريديوسنج للبارامترز، ودي التريك. انت عملت ريديوسنج بارامترز، بس ايه الماشين اللي انت طبقت بيها؟ ايه الماشين اللي انت طبقت بيها؟ كلاسيكال. and you make classical simulation. فالريدكشن في النمبر اوف بارامترز حصل بسبب الماثماتيكال بروبرتيز بتاعت الهربرت سبيس، ما حصلش بسبب الفيزيكال كوانتم كومبيوتنج. وبعد كده ما تقنعنيش انك انت هتجيب اكيورسي احسن من الكلاسيكال ديب ليرنينج. الكلاسيكال ديب ليرنينج دايما هتفوق عليك. للاسف برضو بعض الابحاث بتتنشر على اساس ان الكلام ده كوانتم ماشين ليرنينج وان هم بيحققوا الكوانتم ادفانتج. there is no quantum advantage. طيب السؤال اللي بيطرح نفسه، ليه الابحاث دي بتتنشر؟ لان الابحاث دي مش بتتبعت لمجلات متخصصه في الكوانتم كومبيوتنج، بتتبعت لمجلات متخصصه في الكمبيوتر ساينس. فالمحكمين ما بيكونوش متخصصين في الكوانتم، فالمحكم اول ما بيشوف حضرتك جبت اكيورسي اعلى من اي كلاسيكال ماشين ليرنينج موديل بيأكسبت البيبر. وفي ابحاث كتير جدا اتنشرت ان الكلام ده مش مظبوط. منهم بحث اتنشر في نيتشر تحت عنوان variational quantum circuits are swamped interrupts. Okay. In 2021 we published a paper. In this paper we proved that quantum computers cannot only solve classical problems faster than classical computers, but can solve new types of problems that cannot be solved absolutely, even though these problems are quite simple using quantum computers. ومن هنا بنقدر بنعرف الماشين ليرنينج داتا سيتس الى نوعين. النوع الاول احنا بنسميه كلاسيكال ماشين ليرنينج داتا سيتس، وده اللي احنا ممكن نعلمها باستخدام يا اما الكلاسيكال ماشين ليرنينج او الهايبريد كوانتم ماشين ليرنينج او الاند تو اند كوانتم ماشين ليرنينج. في نوع جديد بقى اكوردنج للبيبر دي اسمه كوانتم داتا سيت. واتس كوانتم داتا سيت؟ Quantum dataset is a dataset that is produced from the sensors of quantum computers, what's called quantum sensing and quantum metrology applications. So you have quantum states that captured by quantum sensors. Can you save this dataset on HPC? Can you do this? Totally no. Totally no. can you learn this using variational quantum sets? Totally no. You cannot do this. So we need a new type of quantum machine learning, what's called end-to-end quantum machine learning. Okay? But what is the roadmap to implement end-to-end quantum machine learning? Or hybrid quantum classical machine learning with quantum advantage in terms of time complexity. أول حاجة لابد من وجود quantum من memory وتكون ليها time complexity أعلى من الكلاسيكال رام عشان نقدر نحقق الكوانتم ادفانتج. تاني نقطة لازم يكون عندنا طريقة نعمل بها الكوجنيشن للنون اورثوجونال ستيتس عشان نقدر نعلم الهايبريد او الفاريشنال او الاند تو اند كوانتم ماشين ليرنينج في بولينوميال تايم. النقطة الثالثة ان احنا محتاجين، دي بقى النقطة اللي احنا يا ريت كلنا نركز فيها، بدل ما نروح لابلكيشنز واحنا متأكدين ان احنا مش بنحقق كوانتم ادفانتج وندعي ان احنا بنقول احنا هنحقق فيها كوانتم ادفانتج، يا ريت نحل المشكلة دي. احنا في الريسيرش بتاعنا حلينا اول مشكلتين. حلينا المشكلة دي ان احنا اخترعنا اسرع كوانتم من ميموري، وحلينا المشكلة دي ان احنا قدرنا نبتكر طريقة نتعرف بيها على النون اورثوجونال ستيتس في البولينوميال تايم. عدنا المشكلة دي. لو اتحلت المشكلة الثالثة دي احنا هنقدر نحقق الاند تو اند كوانتم ماشين ليرنينج وذ كوانتم ادفانتج. دي النقطة اللي هي فيري تريكي. اوكي؟ ده نبذة عن الريسيرش ورك بتاعنا. We developed quantum artificial intelligence systems. We developed quantum algorithms that achieve quantum supremacy, and we invented some systems in quantum blockchains and quantum cryptocurrencies, and we invented some systems for quantum 3D printing, and we proved that quantum computing can solve new types of problems that cannot be solved absolutely using classical computers, and we published 2 papers on this topic. But to handle these challenges, we had to devise 2 key paradigms in quantum computing. The first thing is quantum in memory, and we developed a new quantum approach based on quantum entanglement to reduce the computing time from exponential, as seen in some problems with classical computers, to binomial time in quantum computing realm. So let me explain the second approach. Here, what is quantum state? What's quantum state? Is this entangled state? Is this entangled state? Is this entangled state? هل دي انتانجل ستيت ولا لا؟ هل دي انتانجل ستيت؟ كويس. separable state. good. طب دي اوكي انتانجلد ولا لا؟ ماشي. طب دي انتانجلد ولا لا؟ اوكي دي انتانجلد. اوكي ودي entangled or not? Huh? Not. So. Okay. This is entangled, okay? What about this? Entangled, okay, good. ودي انتانجلد، ايه رايكم؟ لا طب هنشوف بعد شوي. طب what about this؟ مين اللي قال دي انتانجلد؟ انا بشكرك انك انت قلت لي الاجابه دي. انا بشكرك انك انت قلت لي الاجابه دي. للاسف النقطه دي بتبقى confusing لناس كتير جدا، وفي ناس بتمثلها بالاكزامبل بتاع الجلافز بس. this is not entangled state. للاسف في ناس بتقع في النقطه دي وتمثلها بفكره الجلافز اذا كان رايت او ليفت. اوكي this is not entangled state. okay so absolutely this is separable state, not entangled state. And what about this? Indeed, we have a measure for quantum entanglement. We have a measure for quantum entanglement. We have a formula that quantifies the degree of entanglement between any two qubits. This measure, there are many measures. The most effective one for two qubits is called concurrence. So concurrence, we can use this formula to quantify the degree of entanglement between any two qubits. Okay, so the concurrence may be between 0 and 1. So if you apply this formula on this state, it will be 0. Okay? Apply on this 0. Apply on this not 0. Apply on this not 0. So this and this are entangled state. Using this measure, we call this measure concurrence. It quantifies the degree of entanglement. How much entanglement between two qubit state. But can we apply this formula on quantum computer? We cannot apply this. This is a classical formula. So in 2020, we published a paper. For the first time, we say that the degree of entanglement can be used to solve interactable problems. If we can quantify the degree of entanglement between two qubits, then we can solve our problem. This is our model. We have some input state. This state may be prepared in a uniform superposition or received using quantum teleportation or quantum networking. Then we apply some computation. This computation may be machine learning, quantum machine learning, or maybe quantum computing, maybe any problem. Then we add ancilla qubit initialized in state 0. Then we apply an operator is called MZ. MZ create entanglement between these two qubits. Then we measure the degree of entanglement. After we measure the degree of entanglement between these two qubits, we can solve our problem. So you can use this model to develop your quantum machine learning algorithm, or you can develop your quantum AI algorithm or quantum computing algorithm, and you will achieve quantum advantage. But there is a trick here. And when you apply entanglement here, the entanglement may be actual entanglement or maybe virtual entanglement. What is the difference between actual entanglement and virtual entanglement? Actual entanglement means that these states cannot be factorized on all base states. This is the actual entanglement. So if we change the basis, we cannot factorize these two qubits. But there is a situation that these two qubits may be not factorizable in computational basis. So in computational basis, they are entangled. But when we apply some additional operator to make the entanglement between these two qubits is actually entangled, then we can make them actually entanglement. But if we calculate the concurrence before we apply the separator operator, or after applying the separator operator, the concurrence value will be the same. So we don't need to apply additional computation to make them actual entanglement. In this case, we call them virtually entangled. Okay? Indeed, to solve your problems using this model, there are two theorems that says how can you solve your problem. Your problem always given by this formula or this formula, according which the probability of 4 zeros greater than 4 zeros or not. And if the other condition, then we change the solution here. There is another technique. You can use to solve your problem, that if there is entanglement or not. This technique will be useful to solve some problems. And indeed, the time complexity of this model is constant in a predefined error. So we provide this in 2 papers, and we proved that our model achieve quantum supremacy and faster than Grover. We published these papers for the first technique and these papers for the second technique. Also, using this technique, we invented some quantum blockchain systems and quantum cryptocurrency systems and filed these 2 patents. And in last week, we have granted this patent from US Patent Office for inventing the quantum consensus protocol for managing and mining quantum cryptocurrencies. What about main memory? Okay. أنا عارف إن في ناس maybe physics, maybe engineering, maybe computer science، ولكن هتكلم شوية مع الناس اللي هم تخصصاتهم physics شوية. لأن الكلام ده يعتبر basics للكمبيوتر ساينس. إحنا عارفين إن أي classical processing unit، أي computing system بيتكون من حاجتين: classical computing unit and quantum main memory. Sorry, classical main memory, which called the main random access memory. What about the classical RAM? Classical RAM comprises a set of memory cells. Each memory cell is assigned an address. When a classical and RAM communicates classical processing unit through 3 buses. The first bus is called classical data bus, and the second bus is called classical address bus, and the third one is called quantum control bus. When a classical processing unit needs to send or store data to a certain memory cell, it sends its address through the address bus and sends its data through the data bus and specifies the operation as write on the control bus. Subsequently, the data is written to this memory cell. On the other hand, when the classical processing unit needs to read a data from a certain memory cell, it sends its address through the address bus and specifies the operation as read on the control bus. Subsequently, the data is loaded to the classical processing unit through the data bus. What about the time complexity to write to all memory cells in classical RAM? It is exponential. And the time complexity to read from all memory cells in classical RAM is exponential. Okay? And this makes your variational quantum machine learning is exponential. Okay? Because you read your data set from classical RAM. So any steps you do, it's a time complexity exponential. Okay? So when you have a classical AI algorithm that is executed by a classical processing unit, and we have a machine learning data set stored in RAM, then this algorithm is executed by a classical processing unit to train from the main memory. Many firms are striving diligently to develop what's called fault-tolerant quantum computer, and this graph explains their recent work. And recently, IBM announced that they have a clear roadmap to produce the first fault-tolerant quantum computer by 2029. But what about quantum main memory? What about quantum main memory? All firms are working to develop the fault-tolerant quantum computer. What about quantum main memory? Indeed, this motivated us to invent the fastest ever quantum main memory. We call our invented QRAM Q1 RAM. Why Q1? I will explain later. Our Q1 RAM communicates a quantum processing unit through 3 buses. The first bus is a quantum address bus, the second bus is a quantum data bus, and the third is quantum control bus. This is our invented quantum circuit, which has been granted the first patent by 2021, and the second patent by 2023, and the third one last week. The time complexity to write a classical data into our classical دي بقى النقطة المهمة. احنا كده بقى داخلين بقى ازاي الكوانتم ميموري بقى هتدينا كوانتم ادفانتج. اوكي؟ لو انت عندك الداتا سيت بتاعتك الكلاسيكال داتا سيت خزنتها في الكلاسيكال رام. Our invented QRAM can write all this data at the same time and time complexity O of 1, and can read your data set at the same time with time complexity O of 1. And if you have a quantum data set, quantum sensing data set, our invented QRAM can write this data set in time complexity O of 1 and can read it in time complexity O of 1. This is the fastest ever quantum main memory developed so far. Okay? وبالتالي لو انت عايز هنا بقى الكوانتم انتانجلمنت مش هيخلي زي الكلاسيكال ماشين ليرنينج. انت في الكلاسيكال ماشين ليرنينج مش عامل اي اعتبار للمين ميموري ولا عامل اي اعتبار للكوانتم بروسيسنج، لان في الكلاسيكال ماشين ليرنينج مفيش حاجه اسمها انتانجلمنت. هنا في الكوانتم بقى الكوانتم انتانجلمنت ده بيجبرنا ان احنا نعامل السيستم ككل واحنا بنديفلوب الكوانتم ماشين ليرنينج بتاعنا. فبالتالي مش هينفع انك تطور سكيلابل كوانتم ماشين ليرنينج بدون ما تاخد في حسبانك ازاي الكوانتم بروسيسور داخل وازاي الكوانتم ميموري داخله وازاي الداتا سيت بيحصل عليها تريننج. ده لازم ناخده في حسبان احنا بنطور الكوانتم ماشين ليرنينج الجوريزم. ليه؟ بسبب الكوانتم انتانجلمنت. وبالتالي في الحاله دي احنا دلوقتي عندنا بقى كوانتم مين ميموري نقدر نربطها بالكوانتم بروسيسنج المتاح حاليا عشان نبدا نطور الكوانتم اي اي الجوريزم تقدر تشيف الكوانتم ادفانتج using physical quantum computer, not the mathematical probabilities of the Hilbert space using classical computer. By the way, when you achieve By the way, I published in 2029 a paper that achieved machine learning advantage using the mathematical properties of Hilbert space. Okay, but we didn't call it quantum machine learning model. We called it inspired from quantum, مستوحى من quantum, not quantum, because we use the mathematical properties of the Hilbert space. Okay. By the way, دكتور سالم كان بيوضح على الكوانتم سايبر سيكيورتي. طيب لو احنا دلوقتي عايزين بقى نطبق الكوانتم سايبر سيكيورتي على اللارج سكيل، على السكيلبل ابلكيشن. عشان نطبق الكوانتم سايبر سيكيورتي في الحاله دي احنا بيبقى عندنا المسج بتاعتنا هل هي سمول مسج ولا لارج سكيل مسج؟ اللارج سكيل مسج هطبق عليها الكوانتم كي ديستريبيوشن. احنا بنعمل جنريشن بالكوانتم راندوم جنريتور فور اكزامبل، ونعمل انكريبشن للمسج. اوكي، بالتالي هيبقى عندي المسج بتاعتي كلاسيكال ولا كوانتم؟ كوانتم مسج. كوانتم مسج دي حجمها صغير ولا كبير؟ حجمها كبير، يبقى عايزه ايه عشان تخزن فيه؟ كوانتم ميموري. تمام، يبقى لازم تخزن فين؟ في الكوانتم ميموري. هيحصل بافرنج ويحصل تليبورتيشن، او هنقول المسج بتاعتي بالكوانتم تليبورتيشن. هتروح الناحيه الثانيه هستقبلها فين؟ هستقبلها فين؟ لازم يكون عندي كوانتم ميموري. لازم يكون عندي كوانتم ميموري عشان استقبل فيه المسج. اوكي، الدكتور احمد مهدي يمكن عنده كومنت. الداتا كلاسيكال هنحولها لكوانتم عشان اعرف اطبق عليها الكوانتم كي ديستريبيوشن. هحصل على كوانتم سوري كوانتم كي كوانتم انكريبشن كي كوانتم انكريبشن كي. Another technique, yeah, another technique. We have a message, and we developed this technique by the way. We have a message. We transfer our message into quantum state. So you have to encrypt it using quantum encryption key. This key you may be developed by your algorithm or received by quantum key distribution or by any quantum way, and then you have a quantum key, a quantum encrypted message. هتخزنها فين؟ في quantum memory لأن هي large scale. عشان تنقلها الناحية التانية. هنا بقى أنت مجبر يكون عندك quantum memory تستقبل فيه مين؟ تستقبل فيه مين؟ المسج بتاعتك عشان تقدر بعد كده تفكها ويتحول. يبقى إذا مش هتقدر تطور سكيلابل كوانتم سايبر سيكيورتي بدون الكوانتم مين ميموري. الكومنت بتاعتك واضح يا دكتور احمد؟ طيب yeah, if you use register, how can you manage them? And this issue is announced by IBM. IBM developed what's called quantum-centric quantum computer. They perform some operation on Fukugo supercomputer and another operation, another operations using quantum processing unit. Okay, but and they explain this problem. They have not a way that connect the calculation that was performed on the Fukugo by the quantum computer. So they made this operation manually, and I will send their video that explains this problem. Our quantum RAM solves this problem to manage the operation that will be performed on Fukugo, and then you try to apply on quantum computer. I will. Okay. So quantum registers can be used for small scale. You cannot use for large scale. So even though classical computers or our cellular phones, they are work based on RAM, not classical registers. Okay. What is the second comment? Okay. This is a very good question. Yeah, there is a difference, and we invented one for quantum communications, and this was the third one. We invented this quantum memory especially for quantum communication, because there is a difference between the processing for quantum computing. Yeah.
But my second question is, do you see that we will reach fault tolerant or we will not reach?
When IBM produce the fault tolerant quantum computer, our quantum memory will be ready for this.
Yeah, but we have our own path. We know what we...
Give me small seconds and I will explain this. Okay. This is for quantum cybersecurity, also for quantum teleportation. What about if you need to teleport a bulk of qubits? Not in small individual qubits, not small qubits. What about if we have a bulk of qubits? We need to teleport them. Also, quantum memory is desperately needed. Okay. By the way, American company from USA was communicated us to use our invented QRAM to develop their quantum bioinformatics system. في شركة في أمريكا لما عرفت إن إحنا عملنا الQRAM اتواصلوا معانا وطبقوه وبيحاولوا فعلا تتطبق عندهم في الquantum informatics systems. This is IBM implementation, Dr. Ahmed. This is the IBM implementation. We implemented our invented QRAM. There is one invented by 2008 by Sisloid. Do you know Sisloid? He is a famous professor at MIT. Sisloid invented the first main memory. It's called bucket brigade. Okay, but he invented to work in qubits, not qubits. And some Canadian researchers transformed it to be implemented using qubits. And when IBM opened their quantum computer for us last year, we implemented our invented QRAM and compared with bucket brigade, which was invented by Sisloid, and our invented QRAM achieved a quantum supremacy by 751%. This is on IBM quantum computer. Also, we compared our invented QRAM with 16 gigabyte classical RAM. We implemented our QRAM using IBM quantum computer and compared with the time of 16 gigabyte, and this is the supremacy. We published some papers to use our QRAM to store data that is captured from the astronomy. And this table explains our invented QRAM. This is a very important table. This table explains our invented QRAM compared to all other QRAM architectures. If you see for the time complexity to access all memory cells, our invented QRAM is the fastest ever quantum memory. And for all other applications, for other functions that are related to writing data and reading data, some of these cannot be performed. But our do all operations. So our invented QRAM is the fastest ever quantum memory and the most efficient. دي برضو كانت يعني استوقفتني مقولة معالي وزير التعليم، بيقول أنا لو بقيت رقم 1 في التصنيفات البحث العلمي عالميا ومش عارفين نصنع إبرة ما يهمنيش. أنا مش هدفي كده، هدفنا الوصول للبحث العلمي يصنع ويطبق ويحل تحديات. عند اي اجري ايه فايده ان انا اطلع مليون بحث مش عارف اطبقهم في الواقع؟ ايه الفايده؟ ايه الفايده ان انا اعمل 10,000 براءة اختراع وانا مش عارف اطبق واحده فيهم في الواقع؟ So the research must be implemented. الحقيقه احنا عملنا ديسكشن مع IBM وهم مشكورين نصحونا ان احنا نعمل الستارت اب بتاعنا. الدكتور شيشه I think you know دكتور شيشه he recommended us to build our startup for quantum memory. والحقيقه لما بدانا لقينا في دعم، يعني لقينا الدعم من الزملاء الدكاتره جوه مصر وبره مصر والباحثين دعمونا ان احنا نبني فعلا الستارت اب اللي تحول الكوانتم ميموري الى برودكت متاح النهارده نقدر نستخدمه النهارده. وفعلا طلعنا بيه ابحاث علميه وفي شركه في امريكا بتحاول ان هي تعمل بيه كوانتم انفورماتكس. طيب ازاي حولنا الكيورام؟ هنا بقى لما دخلنا للصناعه بقى لقينا في حاجات ميسنج، في حاجات ما كناش واخدين بالنا منها. تمام؟ زي حاجه بنسميها الكوانتم جيت واي في الريل تايم. لقينا المشكله دي ما اتحلتش ولا حد فكر فيها. ازاي يكون انا عندي داتا جايه من اي او تي سيستم في الريل تايم واخزنها عندي في الداتا سيت في السوبر بوزيشن؟ دي بروبلم ما حدش كان فكر فيها ابدا. ودي ما اكتشفناش غير احنا بنطبق نحول الكيورام الى برودكت. وعملنا فيها اختراع في الكوانتم جيت واي، فبالتالي اصبح دلوقتي عندك كلاسيكال ماشين ليرنينج سيستم I know the time okay so it can be provided to our quantum gateway then can be develop your quantum machine learning using this hybrid system and we develop the ecosystem and this is the website. The website here have 3 options. You can try it for free for non-experts. لو انت مش عارف اي حاجه في الكوانتم كومبيوتنج ده ديمو بيساعدك ازاي تعمل اي حاجه لو انت حتى مش عارف اي حاجه في الكوانتم كومبيوتنج. ده بقى للديفلوبرز والريسيرشرز والكوانتم كومبيوتنج. احنا بنوفر بلاتفورم تقدر تنتجريت الكوانتم ميموري بتاعنا في الالجوريزم بتاعك انت بتطوره او في البرودكت بتاعك انت بتطوره وتقدر تطبقه على كوانتم كمبيوتر حقيقي او على سيميليتور. كمان بندي لك اي بي اي لو انت مش عايز تطور الالجوريزم بتاعك عندنا، الالجوريزم بتاعك مثلا سري عايز تخليه عندك، احنا بنديك اي بي اي تقدر تطبق عندك على البلاتفورم بتاعتك وتقدر تنفذ سيمسلي يوزنج اي ريل كوانتم كمبيوتر او اي سيميليتور. وفي الاخر بندي لايسنس لاي شركه عايزه تصنع كوانتم كمبيوتر. برضه احنا لما طورنا الكيو ار رام هو fully compatible with كيسكت. الكيو 1 رام compatible totally with كيسكت. اوكي؟ وبالتالي مش هتلاقي اي صعوبه انك انت تطور الالجوريزم بتاعك باستخدام الكيو رام. ده الكيو ار كود لو حد حابب يجرب السيستم. ثانك يو.
بنشكر دكتور محمد. Thanks very much Dr. Muhammad for this nice talk and also the impressive works and the presentation indeed.
He is a member of QEDC and Qualcy. Also, he is a founder of QuantLane SASU and Allen Quant LLC. Also, is offering management consultant in and AI services. Now the talk for you, Ala.
Thank you, Asma. Thank you to the organizers. Thank you to all participants for having me remotely. Taha will help me present my slides. It will be dense and short, 30 minutes, and hopefully I will be able to make a demo throughout this presentation. So
they can see your slides, Alan. So they can see your shared screen as well as your video.
Excellent. So let me share that this presentation, the opinions and statements are mine as President Molketsas. It's worth noting that I've been a Qiskit advocate since the end of 2021, so I have a bias in favor of IBM offering, especially IBM Quantum, And besides, I'm also, as you can see on this slide, a co-author of a book which came out in 2022, titled Quantum Chemistry and Computing for the Curious, illustrated with Python and Qiskit code. And I'm an international speaker. I'm proud to share with you that I've been invited as a participant to the 2025 IBM Quantum Developer Conference in Atlanta in November this year. And I was also a participant in last year's event in Poughkeepsie. So for more details, please check my details on my LinkedIn profile, where you can reach me, by the way. Can also be reached, of course, on the Discord channel for Qiskit. Okay, so I will present an overview of the so-called sample-based quantum diagonalization, SQD for short, which is an algorithm which is very promising. And I will illustrate this promising algorithm with Jupyter notebooks, which I've published on GitHub. It's a public repo, and feel free to access it. Okay. This is the agenda. So first of all, I will put SQD in the context of the quantum-centric supercomputing, and then introduce what SQD is about, followed by two very interesting use cases, and finally, if time allows, a demo which reproduces one of the use case. Okay. Oops. So what is quantum-centric supercomputing? So it's a term coined by IBM, and this is the definition. Quantum-centric supercomputing is the future of high-performance computing and is the way to achieve near-term quantum advantage in chemistry, materials science, and other scientific applications. So this is extracted from a press release. IBM and Pascal initiate collaboration to define classical quantum integration for quantum-centric supercomputers, was back in June of last year. Technically, a quantum-centric supercomputer is comprised of, guess what, quantum processing units, graphical processing units, GPUs, which are now the component of high-performance computers, and CPUs. And we hold the view that this quantum-centric supercomputer is the key to unlock the next generation of computing. So don't, I mean, it matters to view quantum computing as a key component of a wider offering quantum-centric supercomputing, okay? Now, what is sample-based quantum diagonalization? So I've extracted a definition which I think is easy to understand, and I quote: sample-based quantum diagonalization is a chemistry simulation technique. Well, that's what it was designed for at the beginning. Nowadays, we see opportunities of extending the application beyond chemistry. It uses the quantum computer to extract noisy distribution of possible electronic configuration of a molecule in the form of bit strings. So yeah, so basically the quantum computer is used as a sampler. Then the SQD runs a classical iterative correction, which is like, it's actually an error mitigation technique, but a smart one, which basically leverages knowledge of the physical properties of the system, typically symmetries, okay? And so there is hope and hints already that for large enough noisy quantum computer with low error rates, that this SQD algorithm has the potential to perform more efficiently than classical approximation methods. So it's worth mentioning that in the last couple of months and weeks, a number of papers have been published with variants of this SQD. And yeah, there are a number of posts. I would mention those by Jay Gambetta, for instance, on LinkedIn. Every week or so, there is a new paper coming out, a variant of SQD. So this is a very important algorithm. Oops. Yeah, so this is a zoom on the recovery loop, which is again error mitigation based on knowledge of the properties of the system. So it is illustrated on the right-hand side, and on the left-hand side there is the explanation. So first of all, on the left-hand side, on the right-hand side, the diagram shows a psi, which is a symbol which stands for a wave function. So we start with an ansatz. So it's a so-called LUCG ansatz. There is a definition, by the way, in the glossary, which is included in my presentation. So yeah, so the LUCG ansatz is at the moment a good compromise between the is to run a circuit, quantum circuit, and the challenge of having a very accurate a circuit which very accurately models the physical system. And so what's worth noting is that the unlike other methods that have been presented before, like the variational quantum eigensolver (VQE), the sampling is done only once, and the iteration, and there are iterations in the recovery loop, is done classically. So there is a big difference with the VQE algorithm because there is no gradient descent involving a quantum circuit. Okay, so the trick is to basically every quantum physics system, and in particular those pertaining to Hamiltonians representing molecules, chemistry, it boils down to solving a big algebraic linear algebra problem. Basically, it boils down to diagonalizing a big matrix. The issue is the matrix is so large that even the most powerful supercomputer, it cannot be achieved. So this method, based on sampling by a quantum circuit, the idea is that instead of having to or trying to diagonalize a huge matrix, instead it boils down to solving a number of smaller diagonalization matrices. So this is what is shown on the right, and this is, by the way, this was a topic in one of the labs of the quantum summer school, and so maybe some of the participants have already seen this in practice. So let's see the reason why this is the future as compared to, at least for chemistry applications. So in this, on the left-hand side, you see a table which summarizes the challenge for the iron-sulfur cluster simulation on today's noisy quantum processing units, even the best ones. It's estimated it would take 3 million years to properly find the round state with the accuracy which is required to deliver value in the quantum chemistry arena. So definitely hopeless. Okay, with a much more promising and theoretically proven algorithm, the quantum phase estimation, on a fault-tolerant QPU, which we expect to have by the year in 2029, in a couple of years, it would still take 13 days running continuously on a fault-tolerant QPU. Well, that is beyond what is really practical because, yeah, it's in practice, unfortunately, even with the fault-tolerant QPU, it would be really challenging to run a calculation for such a long time. However, the very good news is that there has been experiments that have shown that SQD within a quantum-centric supercomputing framework, it only takes 2 hours to properly simulate the iron-sulfur cluster. At the bottom, I give the references. This is a very good result achieved by IBM, Cleveland Clinic, and Riken, who gave access to their Fugaku supercomputer, which is one of the most, if not the most powerful supercomputer available in the world. So this, in a nutshell, explains why it's worth nowadays focusing on SQD as compared to VQE or even QPE for quantum chemistry. Okay. The other very exciting use case, a collaboration by Lockheed Martin and IBM to conduct chemistry simulations to simulate the dissociation of the ground state triplet and first excited single states of methylene, which is the formula CH2. So their study is relevant for interstellar studies and also for combustion, for improving the performance of engines. So on the left-hand side, so I've given credit for the images, but what's interesting about this methylene molecule is that it oscillates between 2 different states. And we'll look at that into details. There are 2 different configurations, the triplet and the single state. Okay, and it is important to properly model this behavior. Okay, so on this side we see also that this study, which was made back in 2024, the researchers used the one of the best quantum device offered by IBM, and at the time it was 52 qubits. It's worth noting that during the quantum summer school and currently with the free plan, which is offered by IBM Quantum, anyone can access a much more powerful quantum device. Actually, 2 of them at the moment. I think there is a so-called IBM Brisbane, just a nickname for a quantum device, which has got 127 qubits, and IBM Torino, which has got 133 qubits. So bear in mind that when you add 1 qubit to a quantum device, in theory, at least you multiply the quantum volume by 2. So there is a huge difference between 52 qubits and 127 qubits. So it's amazing. It shows the speed at which there is progress in just about a year. Anyone, I will show you in my demo, can replicate an experiment with which is still cutting edge, but which much more powerful hardware. I think it's extraordinary. So in this slide, try and illustrate why, I mean, the gist of this experiment. So what the researchers achieved was to accurately capture the so-called first-order phase transition between the singlet and triplet states of the methylene molecule. So on the side of the diagram, so basically there is a between a carbon atom and a hydrogen atom, there is a bond, and the length of this bond can vary a bit, and what happens is when it changes, there is at some stage shown on this picture, there are several simulations, and for each one you see the triplet and the singlet. At some stage, the 2 curves, but in the same simulation, they cross they cross one another, and this is where the model predicts that there will be a first-order phase transition, and so it matters to do that accurately. And the researchers claim that with the SQD within the quantum-centric supercomputing framework, that is not just the best quantum processing unit available, but also together with the powerful Fugaku, I think it was Fugaku supercomputer. They not sure actually. Anyway, they managed to outperform or at least show results that do compete with the best classical simulation. Okay. So now it's demo time. So I will introduce the first demo. So it's to find an approximation to not just the energy of the ground state, but also the configuration of the electrons for the so-called carbon single state. So on the right-hand side, you see the single state. The two electrons of the carbon are paired, and one orbital is empty. And there are two possible configurations. Whereas at the bottom of the diagram, on the right-hand side, you see the triplet. The two electrons are in different orbitals. And in the single state, the two electrons are paired with opposite spins, which results in a total spin of 0. Okay. Whereas in the triplet state, I will show you the triplet state. So hold on, I will show you the triplet state before I move to the demo. The carbon's outer shell, there are two unpaired electrons which have parallel spins. So it leads to a total spin of 1. However, now this is just when I make the demo, with PyCF, which is a popular tool by Sensor Python for simulating chemistry, with PyCF, the spin parameter pertains to the number of unpaired electrons. So in the demo, we'll see a spin of 2, whereas actually, strictly speaking, it's a spin of 1. Okay, so now I will go back to the demo. It's actually, I will click there to show you that it's actually available on my public repo, SQD Alain. So this is the nice Gradio-based interface. I will try and demonstrate it now, so bear with me. So, I don't know. Yep. So I've prepared this. So this is a Jupyter notebook, and it's well documented. So basically, I will run it live. So I restart the kernel. Okay, and I run everything. Okay. So it just executes one Python script. Okay. It should do something very soon. Yes. Okay. So by the way, it uses the latest and greatest Qiskit version 2.1. So now I'm invited to open this. And you see, this is the radio user interface. So I've got the name of the file where this experiment is saved. So I will load it. So it refreshes everything. So just to illustrate that it's very easy for anyone who is interested to replicate the experiment, you just have to run the Jupyter Notebook, click on this button to load the configuration, and you see there where there is the formula CH2. If you want to run on an actual quantum processing unit, you just click there, and there you see it shows a drop-down list box with the IBM devices I'm allowed to use. And this is not hard-coded in the code, so that folks who have access to different sets of quantum devices would see whatever they are entitled to use. And in the future, if there is a new device, which will happen soon, you would see this drop-down list box updated. So none stands for least busy, and there is the okay. So this interface lets you actually run on actual quantum devices. And when everything is ready, and I could change some parameters, but they are already preset, I just save the configuration again, and it is running. If I look there, I can see a more detailed log of what's going on. And so it takes a while. This is not my most powerful laptop, by the way. So you see, it has done some computation. It's computed the classical energy classically. You see the number of qubits, 26. It's beyond what can be simulated with the simulator on a laptop with I only have 32 gigabytes of memory available for Ubuntu. So what happens is this is achieved because there is a trick. Instead of attempting to simulate with air simulator, which is a powerful simulator, the running of a quantum circuit, what we do is we use a nice function which generates 10,000 samples drawn from the uniform distribution, which is, of course, much worse than what we would expect from an actual sampling from a quantum circuit. But you will see, I mean, at least that's what the demo shows, that the recovery procedure is so efficient. Even if we start with the worst possible configuration, uniform distribution, at least for small molecules, then it works. And of course, this is the advantage of this work of mine, which is, by the way, based on it's. I give credit to the original author of the work from which my work is derived. But basically, with this interface, you can experiment comfortably, I would say, on your laptop. And then when you feel confident that this is running fine, then you can try and run it on a real quantum processing unit. So it takes a while. So while it is doing that, I will just show you the results what we have with the triplet. So with the triplet, it's the same. It's very similar, except that there is a spin. Again, it's the number of unpaired electrons, which is 2, but otherwise it's very similar. Same, of course, formula. And yeah, it takes, the post-processing takes some effort, even on a fairly powerful laptop, and it does converge after, I would say, 160. So it's about 2 minutes and a half, I would say, and it does converge. So this was achieved on another laptop of mine. So the thing that we see, it starts improving from one iteration to the other. What I would like to show you is an illustration of what has been done with nitrogen, which was, by the way, a use case for the quantum summer school. So using a bit string from a previous run, this is what we achieve. So in other words, that replicates what we would get by running on an actual quantum processing unit. And what I've done, so you see, after 9 iterations, this SQD, which is the level of accuracy, so-called chemical accuracy, which is 10 to the power minus 3, 1,000ths. But remember that this accuracy has been estimated. It's from a classical calculation. Okay, and if I start with a uniform distribution, so you see it's worse. Eventually, after 12 iterations, starting from a uniform distribution, eventually it does converge. But you see, so that there are limits to what can be achieved with starting from a uniform distribution of bit strings, as opposed to starting with a better quality one, which is you would get from running on an actual quantum processing unit. Okay, so we can have a look, see what's going on there. So you see it has done 2 iterations. Okay, so in the interest of time, I will go back to my presentation, and basically that's it. That's what I wanted to show. That the amazing progress which has been made in less than a year, and the ability to replicate a very promising experiment on a laptop, and with the opportunity to run it on a quantum processing unit, which you can access. The free plan provided by IBM Quantum lets you have up to 10 minutes of runtime on an actual QPU per month. Okay, so just to mention that those of you who are not necessarily experts in quantum chemistry, don't worry, there is a glossary of terms which explains the basics. And if you want to dig in more, there is an extensive bibliography of everything which is about SQL. So this concludes my presentation. I don't know how we are doing with time, but if there are any questions, I'm available.
Yeah,
Okay.
Thanks, Alain, very much for the nice presentation and also the nice work represented in the demos. So people are clapping here at the presentation. I don't know if you can see the camera, but we have a question here.
Yes, please go ahead.
Yeah, thank you very much for a very interesting talk. Actually, for me, the SQD, the sample-based diagonalization or quantum diagonalization is very new to me, so I'm so interested. So actually, I'd like to know if you can kindly tell me, like, what's the difference here, or what's the advantage in comparison with the variational quantum eigenvalue solver? Especially in the variational eigenvalue solver, usually there is some constraints on the Hamiltonian, that the approximation has to be polynomial. Otherwise, you won't get the speed up. So is this kind of constraint also there on the this sample quantum-based diagonalization method?
So I would just show again this slides. I hope you can see it. Can you see it? Yes.
Yeah.
On the left-hand side, I think it summarizes well the challenge. VQE is still a promising approach, but unfortunately for quantum chemistry, and this is also well explained in the book which was published in 2022, it turns out that because there is a need to map fermionic Hamiltonian to a bosonic Hamiltonian, so there are different methods, but there is a cost for that. So and it turns out that the number of quantum circuits that must be executed it grows with the complexity of the system, i.e. the number of electrons, basically, and also the depth of the quantum circuits is huge. It's beyond reasonable, basically. So the number of gates with VQE, at least what has been documented so far, and I refer to my book back in 2022, it's not reasonable because of the depth. And you see on the left-hand side, it turns out that best experts have estimated 3 million years to simulate an ion sulfur cluster. Now, in my book, we only simulate fairly simple molecules like H2 and lithium hydrate. So, okay, it works, and you can successfully run it with Qiskit nature. Well, so it does work, but in practice, if we, and this is the aim, this is the reason why there is so much work around quantum computing. If we want to outperform what can be achieved classically, even on the most powerful HPC system, then we have got to use another approach. And SQD and variants are much more promising. And by the way, there is a recent publication which shows that there is a hope also that SQD could be used not just for quantum chemistry. So if the Hamiltonian, if basically the solution is within a subset of the whole Hilbert space. So open it, but again, I mean, look at the left-hand side. I mean, VQE for the ion sulfur cluster, 3 million years, whereas today, 2 hours on a within a quantum-centric supercomputing framework. So I hope it answers your question. Thank you for this question.
Thank you. Just yeah. So I mean, sorry, just quick follow up here. So can we get some bound on the complexity here, or is it difficult? I don't know.
It would be opening Pandora's box, but yeah, we can have a follow-on discussion. Say, for example, on one of the Discord channel for Qiskit, for example, and but yeah, I mean what we knew from back from 2022 basically is that for not so large molecules, in terms of complexity, it's exponential basically. That's the problem. So the challenge we face classically, we have got a similar one in terms of the number of circuits and the number of measurements. So for each circuit, we need to make at least 1,000 measurements, and so because of this, the cost of mapping from fermionic to bosonic Hamiltonian, it boils down to and it is made even worse because well, the annoying thing about VQE is that the gradient descent is done classically. It's not done quantumly. So it turns out that issues have been found, well documented, barren plateaus and the like. So it's a combination of things. The quantum circuits, their depths much too large, completely unrealistic, and made even worse by the fact that the gradient descent sometimes fails. And because with the gradient descent, it's an NP hard problem, by the way, and the gradient descent in VQE is done classically. So for all these reasons, it's hopeless to use VQE at least for the purpose of doing meaningful quantum chemistry simulations. A much more promising algorithm is quantum phase estimation, but it's maybe, hopefully, with the error-corrected quantum devices that IBM promises by 2029, maybe we can make some interesting experiments. But still, on the left-hand side, you see for this iron-sulfur cluster, 13 days on the fault-tolerant QPU, 13 days. I think it's beyond what we should reasonably expect in terms of duration of. And if you interrupt the computation, of course, with QPE you can have mid-circuit measurement and the like, but it means it would not be a pure QPE algorithm. Would be something that would try and work around the difficulty of having to run for such a long time. So that's all I can say. Please refer to the excellent video by I think it's Antonio Mezzacapo. Yeah, and it's in my bibliography. He explains very well why SQD is very promising. Okay.
Thank you. So comment. Can we get access to your book? Is it available? We can access or yeah.
Oh yeah, I mean the book is offered unpacked by Pack Publishing and also on Amazon, and even better, there is a unpacked GitHub repo. There is a set of so-called companion Jupyter notebooks, and so whoever purchases the book is entitled to download a set of so-called complete Jupyter notebooks, which is basically an executable version of the book. The lead author is Dr. Kipalen Sharkey, and I'm the co-author. Basically, I'm the one who made the Qiskit and Python illustrations, and so there is a cut-down version of the Jupyter notebooks, which is publicly available, and on my repo, you can check on my repo. You will find a. So I guess I can show you actually, because we share. So let's see. Yes, if I share, you should see. Okay, here you see. There is the quantum computing for the curious. Okay, so this is a fork of the original publication by publishing, but I've tried my best to maintain it. So you can even run again the examples given in the book with this version, which is still work in progress, with the latest and greatest release of Qiskit. So,
and feel free to send us the link so we can forward it now to the attendees here. And we have another, just to have another question. Yeah, just please make it quick. Raise your voice so we can hear it, and then I'm gonna transmit it again.
Yeah, so I think I can share it maybe in a chat of the Zoom. Let's see. Not sure. I will stop sharing, and I will put it in the chat. Okay. Okay. Oops.
Hi, can you hear me?
Yes.
Okay. So you mentioned that instead of air simulator, you used a specific function that was more efficient in simulating your SQD. So can I know about this function or what?
Yes, so it's a function which is available out of the box. I think with it's so I didn't write it. It's available as part of the I think SQD add-on, and I suggest you check my Jupyter notebook and you will see the link there. Let me share on the chat the link to the I just share the so yes, it's a function which generates a set of samples, uniform distribution. So very
okay, thank you. So another quick question. Does SQD need like a specific version of laptops to run?
Well, in practice, yes, because and I've got laptops which I've got so I'm running Ubuntu under Windows, and there is 32 gigabytes out of 64 which are dedicated to Ubuntu, and yes, for that kind of simulation, you're better off to have a fairly powerful laptop. Otherwise, it might take longer. It may not even run. You see, even the classical computation with this so-called 6-31G basis, I refer to my glossary, it might fail. So even the classical part, before we go to the actual SQD, the recovery loop, the classical evaluation estimation with PySCF might fail if you haven't got enough memory. So the answer is yes, you need, I would say, ideally 32 gigabytes of RAM to be comfortable to run that.
Just for the sake of time, we would like to thank Alain Chancey very much for
Thank
the
you.
nice work and nice discussion, nice presentation.
Let's welcome Dr. Hani Ali. Dr. Hani Ali is the senior measurement engineer at Quantware. He holds PSC in electrical engineering from Suez Canal University, then MSc from in microelectronics from Paris. After that, now his experience is mainly related to quantum computing. His PhD title is service code superconducting quantum processors from calibration to logical performance. His talk today is about how to establishing the first quantum computing lab in Africa. Welcome, Dr. Hani.
Yeah, hello everyone. I'm so happy to be here. Do you see my pointer and do you see the slides? I'm trying to move the pointer, so do you see the pointer at least?
Yes, we see it.
Okay, perfect. So hello everyone. I'm so happy to be here today. I'm Hani Ali. Well, let's cut the introduction down. I did my PhD at TU Delft, where I focused on calibrating and characterizing superconducting devices. My focus was implementing a distance resurface code based on the surface code architecture and superconducting transmon qubits. Today, I'm excited to talk about establishing the first quantum computing and sensing lab in Egypt, I would say in Africa, because up to my knowledge, I don't think there is actually a quantum computing lab in the whole African continent. So I'm very excited about this. I think this gives hope to the younger generation to join the quantum race. Quantum is one of the promising technology, as I will show later, and we are in talks with some key profiles in Egypt and some key professors, which hopefully will help us establishing that lab and keeping the expertise of quantum in Egypt to grow and working on multiple area or multiple aspects of the quantum computer, as I will explain in my slides. So let's get started. So many people believe that the next technology, the next computer will be based on quantum. This is an opposite to classical computers, which information are encoded into zeros and ones, while in quantum, this is a computer that performs processing, encode information based on some quantum mechanics phenomena, such as quantum superposition and quantum entanglement. You probably heard of it in high school, and if you're a physics student, you probably heard of it in your undergrad study or your master study. So I won't dive deep into the meaning of these, but I will try to give an introduction to the general audience who may not know what is a quantum computer. So this is a fast comparison between classical and quantum computer. So the basic units of information are represented in zeros and ones in the classical computer. On the quantum computer, it's a bit different. It's normally like a sphere, and the information are encoded in zeros and ones and combination between zeros and ones, what we call quantum superposition. This gives a lot of computational power for quantum, as you have so many states, but also gives a lot of degrees of freedom where noise can be introduced. I will come to this later. The basic unit of a classical computer is based on transistors, actually from the 50s and 60s, where people developed that. And now we see, even in your hand, you hold a computer, believe it or not, that your smartphone is actually a computer, a very good computer with respect to the ones that we were developing in the 80s and 70s. And now quantum computer is more or less like the 70s and 80s of the previous classical computer period. So we are still, like, quantum computers are very big in size, they are not optimized, they are still at the proof of principle experiments. There are many platforms for quantum computer, many physical platforms where this information is processed and encoded and so on. One of the very interesting ones, or one of the many famous platforms, is the superconducting qubits. They have different families. You probably heard of transmon, fluxonium, and other types of qubits. There are also other ones using ion traps, using photonics, using different types of physical platforms to have this quantum phenomena on a micro scale or in a macro scale. The error rate for classical computers, they are quite low, extremely low, actually, extremely rare. This is 10 to the power minus 18 at best. So this is like a it's very, very rare to get an error on classical computer. In quantum, as I explained here, since you have a sphere, you have a lot of degrees of freedom, especially the phase degree of freedom, where errors also can be introduced. So it's a lot more fragile. The best error rate so far, physically, I would say 10 to minus 4, or on average, it's actually 10 to minus 3. So it's very fragile. Like it's likely every 1,000 computation, you get an error. So this is not a reliable computer, right? If anyone from computer science here would laugh at me if I say every 1,000 computation we have an error. This is like very, very fragile. So there are many techniques to improve that error rate, or actually to decrease that error rate to perform as good as the classical computer. We are not yet at this stage. There are a lot of proof of principle experiments that try to improve that error rate. Or when I say improve, I mean decrease that error rate. The source of error on classical computers, they can be from the clock jitter or background radiation. But as I said, these are very rare events. In classical computer, on quantum computer, there are many sources of errors, such as temperature fluctuation, microwave background, and also environmental noise, electromagnetic noise, and so on. So it's a lot more, it couples a lot to the environment, and since it has a lot of degrees of freedom, you also introduce all these errors. So that's why it's a lot more fragile. That's why we need error correction, especially for the quantum case, because we know no matter what we do, an error will happen. So we better think, what if an error happens? And that's what you heard that's what you hear like an error correction term for. So since we know that an error will happen no matter what, so what we are trying to do is to detect when an error happens, and when an error happens, detected and then therefore corrected, or even both selected out. So we would like to have an error detection and therefore error correction, where we can then improve our error rate. People imagine doing this, like imagine you have a key and you want to save this key. So you create so many copies of that key. And this is what we are trying to do here. We create so many copies of the state that we want to protect. And we call that, so the state that we want to protect is encoded in physical qubits. And what we want to create is something called logical qubit, where we create all these copies. And even if error happens throughout the computation, because of this redundancy in the system, you will be able to retrieve the good state. So this preserves your ability to process and encode the right information. Okay, here is one example for the classical versus quantum. As I said, the quantum is encoded on something like a sphere, where often people refer to the 0 state in the top and the 1 state at the bottom. Technically, any point on the surface of that sphere can represent a state. So you can actually already visually see that the computational power for quantum is much larger than the one for classical computer, because you have so many states you can encode here versus only 2 states there. But as I said, it's a lot more fragile. It introduces a lot of noise and so on. So this is essentially, without going too much details, this is essentially what gives quantum computer a benefit to run faster than classical computers for certain problems. So this is with something called quantum entanglement. I will not go through this, but just know the term, and also quantum interference. That gives the quantum computer a vast solution space. Like they can explore a lot of solution in space, because they have a lot of encoded states, they have a lot of computational power, so they can explore much complex problem much faster than the classical ones. So there is a certain class of problems where quantum computer outperform the classical one. So quantum computer will not be used in laptops and will not be widely used everywhere. That's not the point. Quantum computer will be like a laser and a lamp. So the lamp exists everywhere. We use it everywhere. We have a laser which is much more powerful than the lamp, but the laser is being used in certain applications. It's not replacing the lamp. So this analogy works also for quantum and classical. So the classical computer will stay. Actually, part of the quantum computer is a classical computer. As Alan was explaining, we do computation using classical computers. And actually, the better you have a classical computer, the better your calculation is. So part of your what you call a quantum computer is actually fairly classical. So it will not replace the classical computer, but it will be using it in certain applications. And there is a certain class of problems where it's really hard to solve by classical computers. And it is actually the problem when you have when the size of the problem grows exponentially. So for example, you have, I don't know, take any other any simple example, even like delivery. What is the optimal if you have a delivery guy and you want to minimize the costs per restaurant, for example, you have a lot of roads until this delivery guy reaches a target and deliver the food, for example. Imagine like now we want to minimize that problem. We want to optimize the cost. We want to minimize the cost. So there are so many factors that you can take. Like for example, the traffic, the roads, is it ready or not? The gasoline costs, and so on. So the problem, if you think about the variables in this simple example, you will see the problem it grows exponentially, and this can go for anything, like any optimization problem that has so many variations. Classical computers fail to solve the problem if it grows exponentially hard. Because of the computational power, it grows exponentially, so like it takes years to solve. So these are the type of problems that quantum computer promise to solve. For example, a factorization problem. Factorization is the key backbone for encryption in banking systems and military communication. So if you have a large enough quantum computer, it grows actually with like this is a problem that grows exponentially with size. So if you have a large enough quantum computer, you will be able to break some encryption protocols that we currently use for banking systems and military applications. And actually, that's a red flag for all national security people. So that's why people at the national level and governments are really interested in this technology to see where it goes. They know and understand that now it's very noisy, very fragile, but they don't know where it goes in the future. That's why a lot of fund in quantum now comes from the government and comes from armies, and they want to see where this technology is going. Another class of problem where also it grows exponentially and you have so many variations, input variations exponentially, is actually the molecular geometry. As Alan was explaining, these are the type of problems that a quantum Hamiltonian can perfectly describe the chemistry, the physics inside a molecule and inside the atom, because quantum mechanics actually is the running framework, is the actual framework that the atom uses and not uses, but it can describe the atom and the interactions with molecules very well. So quantum can naturally simulate some physics that is running down at the molecular level, and an example was like Alan was showing an example, but there are much more like there are variations of these examples, and actually people can use that. Imagine if we can simulate the chemical interactions between molecules very well, we can very well simulate and develop medicines, for example, that takes years before the medicine is approved, because we need the trial, we need the bed trials, and we need to make sure the medicine doesn't have any side effects and so on, because we lack the tool to develop the medicine and simulate that very well on a classical computer because of the size of the problem that goes that goes exponentially with size, so we cannot simulate it classically. So this is a certain class of problem that would be perfect for a quantum computer, as it naturally mimic the Hamiltonian of these chemical interactions. Another class of problem is the searching over data structure. This goes over everything that you can imagine. This is like an optimization problem that happens. Like if you have an optimizer, if you want to optimize certain things, you have an optimizer that has so many inputs and so many variations, and searching over data structure or whatever the problem is, there is some quantum benefit by running these algorithms on a quantum computer versus that of a classical one. Okay, and there are many others, of course. There is like since we talk about AI, and AI is a hot topic these days, quantum computers can benefit from AI and can actually benefit AI, as in they can be used, AI can be used to, in some decoding techniques for error correction using quantum computers, and quantum computers can be used in data centers to power AI. So they can empower and power AI, which is an interesting topic on its own. So as you see, there are so many applications and dimensions of these where quantum computers can be used. Okay, this is a map of the world and the quantum activities around the world. I want to invite you to look carefully at this map. You see there is a lot of activities in the US, a few activities in South America, a lot of activities in Europe, a few activities in Asia, in Australia, but you see Africa as a continent has no data point. And looking at that, and coming from Egypt, and actually I know a lot of friends who did their PhDs in the domain. They are experts on the field, like in the fields, but they somehow, Africa as a continent is missing the whole quantum activities. And that actually motivated me to contact some professors in Egypt, and there is a lot of work at the theoretical side in Alexandria and in Alamein, and there are other universities who are doing great work at the theory side, also using simulations and so on. But I am just missing this lab, like having a lab there, building the expertise there, trying to teach students how to perform experiments on a physical quantum hardware, and not just using an IBM computer, because using an IBM one, you would be able to run algorithms, but there are a lot of areas of expertise that are missing. You don't acquire that by just running experiments on an IBM quantum computer, which is great. Like it's a great tool, it's great, but it doesn't teach you the lower level of things, like how to understand how quantum computer works, how a hardware works, how to perform characterization, calibration, improve the gate fidelities, and so on. This is something that is missing across the whole continent, and I think we will be making a history if we succeed to get a quantum computing lab in Egypt, because literally that will be the first one, and the students will benefit from that. Imagine master programs where people will be able to perform the experiments, the very experiments that they are studying, and that's much more powerful than running experiments online, which is again very good, but it would be great to have such a lab in Egypt. Okay, what a quantum computer looks like. Here I'm talking about my area of expertise, which is based on superconducting quantum computers. So there are so many physical platforms, as I explained, but I will only cover the superconducting transmon quantum processors. So this is something called dilution refrigerator. This dilution refrigerator is like a fridge in your home, where this fridge can actually achieve a millikelvin all the way down here. So these are different plates, different thermal plates, where they can achieve different temperatures. So you have here the 50 Kelvin, you have the 4 Kelvin, the 1 Kelvin, and then you have the 10 millikelvin. Why do we need this fridge? Because our device works in a very specific energy bandwidth, and this energy bandwidth is often referred to as 6 gigahertz for superconducting qubits. And in 6 gigahertz, if the device works just at room temperature, you have a lot of thermal noise that you cannot isolate these degrees. You have a lot of noise that couples to your qubit, so you don't have a perfect quantum system. And in order to have a quantum and coherent control, you need to minimize the thermal level. So that's why we need such a fridge to cool down the device, so we minimize the thermal noise and isolate the quantum system such that we can use it for computation. There are so many details here on the wiring. There are superconducting wires here that go superconducting below the critical temperature where there is no resistance, because you also need this coherent control with no resistance. Resistance is a way of losses, right? And you need to minimize these losses. So we use superconductivity to minimize these losses and to keep the device cold enough such that the energy levels are well isolated from the environment. At the bottom, this is the quantum device. The quantum device is packaged in a PCB. Here you see two superconducting devices with microwave cables. So these are the cables that we use all the way, like we connect the device to these cables, and these cables carry the signal all the way outside where there is the classical electronics. So the device looks like this. These are superconducting microwave components. You have components for readouts, often called as CBWs. You have components for control. These are the main qubits, the layout for the main qubits here. This is the actual hardware of the quantum device. So this gets fabricated in the clean room. This is a microscale. So the scale here is like, the whole scale here maybe is a few millimeter. You're talking about maybe 10 millimeter or so. So they are fairly big structure with, if anyone is from a clean room background here, like, or uses clean room before, he would know that these structures are quite big, but they are still small with respect to the, it's not centi or meters and so on. They are millimeters here. Okay, these are the control electronics. These carry the signal away from measurement and control all the way down to the device. So the signal is carried out from this, we call that EWG, or signal generators, that transmit the signal all the way down through these superconducting lines all the way to the device here and back. Like we send control signals and we measure back what we see. And then from the data analysis and so on, like there is someone who's sitting behind a computer, who's a physicist or a quantum engineer, who actually performs the experiments and does the coding and stuff in order to understand, perform control experiments to understand about the device, to know what's the device Hamiltonian parameters, to know T1, qubit frequency, resonator frequency, and so on. And also to take actions later and like for next experiments and so on. Okay, this is a full stack quantum computer. So like what I roughly presented here, these I'm presenting it in different layers here in stack. So let's look at this part here. So at the bottom, there's a quantum processor, and then there is a cryogenic and interconnects that carry down the signal all the way from room temperature or from the electronics to the quantum processor. And then there is the classical electronics at room temperature. There is someone sitting behind a computer trying to code and calibrate and control the qubit. And then at the end, there is a quantum application that you want to run. Like this can be the quantum algorithm and so on. So when you submit a job to an IBM processor or any other processor around the world, so what it does, it translates this circuit and this application that you want to run all the way down to these layers. So in every other lab, there are all these layers, and that's what a quantum computer lab is. So you have to have all these layers. Of course, there are so many companies around the world. Here I mentioned the Dutch ecosystem. I interacted closely with these companies, which is actually a spin-off from our group. And here I mentioned the tasks and the challenges for each of these layers. It's not, there are so many details here. It's not very important for now, but just for you to know, a quantum computer is not just one area of expertise. This is an interdisciplinary area that goes from design, fabrication, electronics, cabling, people who know the quantum physics, people who design algorithms, people who do the analysis, and so on. So it's like an interdisciplinary area where it requires a lot of area of expertise. So even if your background is not in quantum, you can still contribute to it and you can still be part of it. And that's my main message to the younger generation here. If you are a student in electrical engineering or communication, you can still contribute to quantum in that way. If you are from software background or computer science, you can still contribute to have or to be part of the quantum computing race. Okay, so let's focus on, let's take what is the technicality and what are the area of expertise that we need to have if we want to have such a lab in Egypt. You at the quantum processor level, you need someone who knows the design. This is electromagnetic simulation using console, using ANSYS, using your own software. It doesn't really matter. But someone who knows electromagnetism and who solves Maxwell equations and can extract the capacitive network of a certain geometry, the geometry-based electromagnetic simulations. There is also the micro and nano fabrication. Anyone who knows microfabrication or nanofabrication is highly appreciated in the quantum field because the device is fabricated using these tools that you would actually normally use for semiconductor industry. So there are actually few clean rooms in Egypt. There is one in the AOC, and there is one in Zweil. I remember there is another one in the national, one of the national labs. So there are people who can already contribute to fabricating a quantum device. Of course, the metrics are different in quantum, but the tools are similar. And then the next layer, you need someone who knows low temperature measurement, filtering, signal amplification, signal noise, signal integrity, like it's mainly signal processing. So anyone with a background in signal processing would actually contribute at this layer here. And then for the control electronics, you need someone who knows microwave engineering or analog circuit design or FPGAs. These are wide area of expertise. You cannot have all these areas of expertise, right? So like it's in quantum, when I talk about quantum computer, like there is like a few hundred of people that are around like when we are talking about Google, IBM, and so on, they have all these area of expertise covering wide range. So they have 400 people that are technically experts in all these areas that cover all these areas. And then there is at the control side, there is like the software engineering background would be highly appreciated, writing software in Python or in other languages like C and C++, writing a modular software that would scale with a number of qubits. It's one of the interesting topics. Also performing data analysis, when you do the averaging, how you extract the f of t of the signal, like analyzing signal in different dimensions and so on, normalizing the signal. And Python is one of the famous languages here. So if you're a young student and you don't know what to do, the first thing I really recommend you to do is to take a Python course. This languages, like coding languages, is like normal languages in science. If you don't know how to speak, then it's very hard to be part of it. So I really recommend the younger generation to learn any coding languages. If you know Python, then go and learn C. If you know C, go and learn C++, go and learn Java, and so on. And then the top layer is actually the quantum, like you need to be a quantum physicist to understand this. So this is about quantum physics, quantum Hamiltonians, the actual details of certain qubits or certain circuits. This is like the top layer of a quantum computer. But even if we have this layer, if we don't have all other bottom layers, then we don't have a quantum computer. So that's a main message here. for younger generations, try to position yourself in one of these area of expertise. And you have wide range of expertise here. And if you like the topic, then you try to position yourself in one of them. Okay, this is roughly if we want to have a lab in Egypt, we want to have the quantum device, the fridge, control electronics, and control software. For device, there are different vendors. Here I'm proposing Quantware with a 5-qubit device. So you are talking about, like, if you know the literature, you will hear people talking about 100 qubit, or even some people talk about a few hundred of qubits up to 1,000 qubit. Here we are talking about 5 qubits, so it's not like a very complex device, but it's a very good device to start with. This is where you grow your area of expertise, where students can learn. It's simple enough so that you can learn already, because you see it's already difficult because of all these different backgrounds that you need to have to establish a lab. For the fridge, there is the very famous one is the Blue Force fridge. There are different type of fridges, but here I choose a fridge that is compatible with the 5-qubit device. And for the control electronics, there are so many FPGA-based control electronics on different companies. Here I'm proposing Q-Blocks. And then at the end, there is a control software, which this is the part that people can and students can contribute to. They can write their own software, but you need the software to control there are different levels of software. There is a software that talks to the machine and controls the physical instruments. And there is a software that is an upper layer that actually performs data analysis. And there is a software that does and perform experiments. So there are different layers of software. Here I'm proposing for the drivers, we would use one that is compatible with the rest of these choices. And students will contribute to that software at this point. And then here I'm mentioning the financial details of these devices. So overall, I don't want to go over the financial technical details here, but roughly it's about 700K in euro. Or yeah, it's up to 1 million, honestly. Like if you count all the other things that you would need, you need an area where there is water cooling, there is an oil pipe, and there is a water cooling pipe, and there is and there is a good enough area to host all these components. And of course you need the technical expertise. You need students you first need someone who knows the thing, and then after you need students to learn, and then the first generation would teach the second generation, and it goes forward. So this is like an open architecture. You can choose to do that with one company like IBM or IQM, or I don't think Google does this, but there is another like you can choose to ask one company to do all that for you. And of course, this is more expensive than doing it yourself, like establishing and ordering it from different companies, and it's about 1 million in euro. So the question to you now is 1 million, can't we afford to have 1 million to spend on a very promising technology to build the area of expertise here? I think the answer should be yes. This is not, maybe this is inexpensive for an individual person, but if you are talking about a country or a continent, Africa is much more rich than 1 million. It should be. And there should be a lab in Africa and in Egypt, honestly, because we have the technical quality. It's not that we don't have the technical quality. We have people who already studied this, and they know that, and they are part of these bigger companies that you are buying the device from. So we should aim to have one lab in Egypt, at least one. Okay, this setup capability can host the 5 flux tunable transmons. This in parallel, you can also measure resonators using something called vector network analyzer. So this can be used for not just for quantum computation, but also for quantum sensing. Students can learn and do experiments themselves. They can learn how to characterize and calibrate a quantum device. They can build their own software on top in order to in order to perform experiments, do the different data analysis, publishing papers, doing research. And then plus, if we have a clean room, we can even characterize our own device. Or if we have people who are their area of expertise are in FPGAs and control electronics, we can even have our own and control, like our own control electronics and our own companies. As you see around the world, there are many startups who are starting at different layers of the stack. There are companies who are specialized in control electronics software, calibration software for quantum, and so on. There are many companies around the world, many startups. And the hope is when you have such an activity in Egypt, you will keep the technical expertise in Egypt. You will grow that expertise over time, and you will have different startups over time. So what you think about this 1 million is not actually, this is an investment, a large investment for a whole country. This is not just 1 million that you spend now and it's kind of lost. The potential of this is millions. If you see the funding raised for different companies now for Series A and Series B funding, you see the evaluation for these companies, startups that started a few years ago, like 3-4 years ago, the evaluation for the company is 300 million and 500 million for different companies, of course. So the potential here is huge. It's not just doing research for fun, but this is growing the area of expertise in-house. At the end, I want to share two exciting news. So this lab will not be visible without someone who knows how to do experiments. And I have some connections with some people in the quantum domain. So I got to talk to a few people, and there are two exciting positions that they could hire for. It's actually the TII in Abu Dhabi. So this is, as I'm working as a consultant there. So I got to know there are two positions. So this is the two positions. If you know the theoretical framework of superconducting qubits, you know the basic knowledge of how to control and measure a qubit. You don't have to have an experimental experience because, again, there is no experimental lab in Egypt. But if you know that and you know Python, you know Git or GitLab, and you know version control for coding and so on, you know, like a little bit of software background, basic data analysis, then this first position is great for you. So you will be learning how to measure a superconducting device on an actual quantum computer. So you will see and deal with all these layers. You will be writing code and understanding the output of a quantum device. The other position is on the design part. So if anyone who knows the theoretical knowledge of superconducting transmon Hamiltonian, James Cumming Hamiltonian, qubit-qubit interaction Hamiltonian, or know COMSOL multiphysics, ANSYS, perform electromagnetic simulations, this will be great. This is another position for you. So TII will be covering all the associated costs, including the flight tickets, the visa-v fees, and salary that cover the living expenses in Abu Dhabi. And the duration of that position is from 6 to 9 months. It can be extended and negotiated. It's at least 6 months. So if you have less than that, then maybe that's not the position for you. If you have at least 6 months to do an internship in Abu Dhabi to learn from a quantum computing lab how to do these experiments, and then ideally these persons and individuals will go back and do the same with the establishing lab in Egypt. So this is a way to kind of create the expertise if we don't have it, like to take the experimental experience if you have it. So if any of you was interested and have a relevant profile, please reach out to me on this email. Only for the relevant profiles I will reply. I'm sorry I don't have too much time to reply to all emails, but I will reply only to the relevant profiles. So if you receive a reply, so you are selected for a higher level interview and so on. So thank you for your attention and happy to receive any questions. Thank you.
Thank you very much, Dr. Hani. And Dr. Hani was kindly shared this position, so I asked him if he can share it with all of you. So if you have the right profile, please feel free to contact him. Unfortunately, we don't have much time for questions. However, on the group, if you have questions or anything, I will forward them to Dr. Hani. So thanks very much again, Dr. Hani, for the nice talk and also this high level of our like understanding the architecture of how to build a quantum computing lab and so on. So thanks very much. And so now I heard that this hall will be closed. I don't know about the time, but I would like to thank our guest again, Dr. Hani, and see you later. Yeah.
Yeah, thank you. Thank you. Bye.
We have now 3 more talks. We are going to start them with, we have from Dr. Sharif and Dr. Yosra and also from engineer Sameh Zaghloul. And then we have a short tour now.
Thank you, Dr. It's now time for the tour, so I think we'll have to catch it outside this hall. And then after lunch we can resume the talks. Would that be okay? Yes. Okay.
So after lunch we are gonna resume the talk. The lunch will be a bit shorter because we have excitement and also excited topics to hear from our speakers.